we have with us Andy Brittain that is going to present to us The Window to the Stars, a model for schools astronomy outreach programs. Really curious, the title is very nice, and looking forward to hear your talk. I'll let you know when your time is coming up, and you can start sharing your screen.
Thank you. I think it should be showing now, but I'll switch over. Can it be seen okay?
We see your whole desktop.
You see, well, let's play that.
We see your presentation, but not in presentation mode yet.
You can't see it?
Yeah, now we see, but we also see the window from Zoom, so you have to minimize the Zoom window. I will also close my camera so that will not spoil your presentation.
I minimize the Zoom window, do I? How do I do that? I'm working on an iPad.
Okay, put in presentation mode again, your PowerPoint.
Are you not seeing it now?
Not in presentation mode. I was seeing the other part.
All right, hold on.
Try again.
I'm trying again. Yeah. Right, so this should be broadcasting my screen. Are you seeing the right thing now?
Yes, we do.
Okay.
But yeah, you still okay, now it's fine. Perfect.
Let's move on.
Go ahead. Yes. Yeah, let's move on.
Yeah. Okay. Right. Well, thank you very much for that. I was drifting into a very deep conversation that you were having there, actually, both of you, and it's a major issue, and my program goes a little bit further than that. So what I would like to speak about is Window to the Stars. I'm Andy Brittain. I'm from Lady Eleanor Hollis School in London. The Window to the Stars is a piece of software that enables students in classrooms to model stars using computer software that's fairly easily accessible, and they learn a tremendous amount of different skills in order to process to run through the programs that the Window to the Stars software enables them to follow. So it's a few years ago when I met up with Rob Izzard. Now, Rob Izzard had a prior career to becoming an astrophysics lecturer, where he worked on developing graphical user interfaces. And so he sort of crossed the divide, mixed up computer aspects with the astro aspects. And he took Peter Eggleton's binary stellar evolution code, which is professional software for exploring the evolution of stars used by professional astrophysicists, and he made it a bit more user-friendly so that students could use it and they can press a button and have it do some interesting calculations. And I'm going to explain a bit about that. My email is up there, as is Rob's, and at the end of the cup, we have a Gmail account that we can be contacted on if you're interested in running this software. A booklet has already been put together that we can send to people. It's all free. The software is free to download, and the booklet is free to be giving out. We're trying to develop materials that we can give out to teachers sort of as we're going through it. It's quite tough. We've got day jobs, so this is in our spare time. We've got lots of other things going on, but this booklet is pretty amazing because it takes through. It's the only booklet I've seen. I'm a physics teacher. It's the only booklet I've seen that takes students right through the process of modeling. And when you look at other programs coming out for developing students' critical thinking and that kind of a thing, what they look at is that students understand that they're working with models and the limitations of the models and the powers of the models. And this booklet takes students through the idea of modeling stars, breaking them down into shells and building it up again, what it's actually trying to show, i.e. the genuine physics behind stellar evolution, and then how the software figures things out, how it actually goes through iterative cycles. So if you follow this program, you can actually teach students an awful lot about the underlying structure, the thinking behind developing some incredible scientific models. And I think they take that forward into all sorts of areas where they can look at the way processes are presented. Unfortunately, in school, I think often we're under too much pressure to really look at the how the models have developed and how they influence the thinking of the students, and that the students should have that extra dimension, that critical thought, which is so essential. All right, and then in the latter stages of the book, it takes them through some projects that they can undertake. There's a bit of programming in there, and then I've put a few things that they could use the software to explore. It runs on a Raspberry Pi. The reason we put it on a Raspberry Pi was because the school networks often had restrictions. The software itself does not require access to the school network, because what it does is it has key features within it that it builds from. So when it's evolve, when it starts to make the star, the starting parameters are in there. And what the student does is change the starting parameters. So the Raspberry Pi is fine. It's isolated from the system. It's, I suppose it could mount up if you get several of these in terms of cost, but we're trying to find ways to supplement that and things like that. But at the moment, we've got funding sources in the UK, but we are trying to find ways of spreading this abroad to support the funding of it overseas. What you see when you open the home screen of Window to the Stars is this thing. And if you take a look at it, you'll see that along the top, you've got various different data presentation tabs where you can look at things like the Hertzsprung-Russell diagram, density versus temperature, structure, etc., which I'll talk through in just a second. You've also got the select starting model options, which is in the sort of the next stage down. And the default setting is about 2% metallicity, that's the Z. And it's actually designed for binary systems, but we currently run it with a single star. So we change M1, and M1 is currently set at the mass of the sun. All right, so this is a stellar mass star. M2 is not currently used with what we're putting out to the students. And in the central set of options, where it says operation mode, initial conditions, initial abundances, etc., as you move to the right, you're looking at all sorts of starting parameters that you can vary. So we've got as far as using artificial physics, but actually there are loads of things you could use, an enormous number. Think of every aspect of a star that a professional physicist could study, and you can change it here. But we're gradually expanding it, because obviously it's only been running for a few years, really. But with the artificial physics option, we can change the energy production through fusion. And so it would look as if the star is suddenly gaining energy, and we'd look at what that does, or if it's losing energy, it's producing less. And that's really fascinating, because that's going to help us model dark energy models and things like that. We could say to the students that let's consider a certain amount of dark energy, excuse me, dark matter that's influencing the behavior of the star, how it behaves gravitationally. What if there's more that's being concentrated around the center of the star? How could that change the energy output? So we can model that. If I move on to the next screen, what I've done here is I've moved from one tab, the top tabs there, options, evolve, Hertzsprung-Russell diagram, row T, I'm going to move through those. So if I move to the evolve tab, this is showing the student the mathematical underpinnings. They're looking under the bonnet of the maths. So the first line will be the starting parameters, which the student can change. And when you press the evolve button, which is there in the center of the screen, those iterations will start to take place. And what the star will do is generate a model that's a little step forward from the starting position. So the initial parameters would be a gas cloud, And the next step forward, the cloud has contracted a little, so the temperature's changed, density's gone up a bit, etc. And then it takes those values and moves to the next step and sees how they influence the values again and again and again. And actually, if it doesn't find a significant change, the software is designed to jump ahead. So it actually, the models that it iterates through are non-linear in terms of time, because if it finds not much is happening for a while, it will move on to the next significant change, and that saves a bit of processing power. It doesn't need to output it all. Now, the next tab along then is the Hertzsprung-Russell diagram, HRD, and that is going to show the plot of this data, okay, from the parameters required for the Hertzsprung-Russell diagram. So on the x-axis, you've got the log of the temperature, y-axis, you've got the log of the luminosity in solar parameters. Now, the beautiful thing about this, one of the many beautiful things, is that the student can watch this growing in real time. Now, normally when we teach this, we just show them a static picture. But what the student would see is the bottom left hand, where we have the starting star. We would see the student will see the plots appear and trend to left, and the student can actually then try and predict what's going to happen, when's the change which is kind of a diagonal line coming down from top left to bottom right. And then the star curves off of the main sequence and goes off into the red giant if it's a solar mass star, and then it collapses down to the left. Now, the time frames for all this are quite spread out, but the student can see it by choosing a label. You'll see there's a label option there. There are loads of different labels the student can put on, but the one that we're using mostly is the timing label, and you can space it as you like, but it will put an age for each point on that diagram, so that the student can see how old the star is at that point, and then calculate how long it spends in which phase, whether it's top right, which is sort of red giant, or whether it's in the lower main sequence stage, how long it spends there. There is a layers option. If you look at the top right, there's a layers option. Now, that's a really great parameter that we're introducing. We've been doing it for a few years now, so we're starting to introduce the layers more. It is in the booklet, and what that allows you to do is to change certain aspects that you want to compare and run 2 or 3 or 4 different stellar paths on HRD and see how they relate to each other. So if you maybe in the earlier screen change the metallicity to be a little higher, you would shift the positioning of the Hertzsprung-Russell diagram plot, and then you can compare it to one that had a lower Hertzsprung-Russell, that had a lower metallicity, and then ask why, what's going on. And you'll see that it's also set to approximate colors, so the student can spot the star changing from a sort of more whitey blue star, whitey yellow star, up to a red star, and then collapsing back down again. And when you increase the metallicity, you may see that there's more blue, for example, and ask the student to discuss that. All these parameters can be shown. Also the radius of the star, so you'll see that the red giant is way bigger than the ordinary star. Moving forward, you can also show the density temperature plot, or temperature density plot. So the student also sees this growing in real time. And on this plot, it's also got boundaries where the star will switch from hydrogen to helium burning. So you can see it happens further to the right here. Suddenly the star crosses the helium burning threshold and starts to change the way it behaves. So it's swelling into the red giant around that point as helium burning goes on in the core. A little bit of that goes on rather than the hydrogen burning, so having a bit of a switch. You can also look at the structure. So the next tab is structure, and I'm keeping an eye on the time, and maybe I don't overdo it. You've got 92 different parameters that you can vary to look at the relationship between them. The structures tab allows you to access all of them. This one shows how the radius of the star changes over its lifetime. Okay. The internals tab, which is the next one, allows you to plot the models in sequence. You can select every 100th model or something like that. And the the nice thing about this particular one is that you can animate through the models or put several models on together. So, for example, in this frame here, you can see percentage of helium versus mass radius on the x-axis, and you see that in the earlier model, you've got about 27% helium content in the star, but by the later models, in terms of mass radius, you've got a way higher amount of helium. Okay, so, and you can actually press the animate button and it'll click through that and the student can get a visceral understanding of how the star is shifting. Now, one thing to point out here is a lot of the models that are given to students are like pretty pictures of spheres and things and, you know, making it all cartoony. This is not cartoony. When you're presenting this to the students, they're pushed to learn how to interpret data as it's presented on the screen and imagine the star itself in their minds, but get an impression from the data, which is incredibly powerful. All this is about structured and development of thinking, the structure of thinking. We also have a Kippenhahn potential graph here. Well, not potential, it's a Kippenhahn graph where we use a third dimension, which is the color. This is a representation of mass radius versus model number. And the student can see that in the early stages, up to about model 200, there's a fairly consistent temperature for the star, around similar color. And in later models, once the stars started moving through the main sequence phase, you get a cooler atmosphere and a hot center. And towards the end of its life, you have a very cool atmosphere and a very hot center. So there's a shift and they can explain what's going on with that. Now, we've advertised this in a number of places. It's now currently on the books at the Lawrence Livermore organization in America. They're recommending this as some kind of sort of extracurricular study material, and the Royal Astronomical Society. We've been contacted by people all over the world, people doing homeschooling, and we want to provide as much support as we can for this. I just wanted to spend a moment speaking. I've got 4 minutes. I think I wanted to speak for a moment about what I did with my kids, my students, so you could see how you could do it with your own students. And we chose this, which is not a great title, but we were sponsored by the Royal Society, who gave us some funding, and we've got a contract set up with them. So in the UK, the teachers can apply using a similar contract. We can give you some help with that. Now, I ran this with year 12s, teaching year 11s, teaching year 10s, teaching year 9s, 8s, and 7. So I got down to 11-year-olds that were working, understanding logs and luminosity and inverse square law. And this is not a perfect piece of text by any means. But when you think that it was written by an 11-year-old who had never studied any science, no astrophysics at all, and hadn't done anything like this, come straight in from junior school, look at the kind of phrasing that she's using. Yes, it's not perfect and it's worthy of discussion, but what an enormous increase in her understanding or the questions she can ask when you consider how she's presenting this. And she's gone on from strength to strength now. It's wonderful. And then you move on to the year 10s and they can take screenshots and take gradients and look at rate of hydrogen consumption, which is what they were doing here. Moving forward to year 11s, and you're seeing the GCSE structure, the exam structure kicking in. Suddenly it looks like an exam piece, okay, examining temperature and density. So these are all teaching each other, all these students. Actually, it's a lower sixth student, well, now upper sixth students, the year 13, who's running this for me, with me sending lesson plans, which means I've been collecting lesson plans that I can send out to teachers once I've sort of tidied them up a little bit. And when you get to sixth form, you give them the equipment and let them run. This is by one student who did all of this, exploring the software to see exactly what limits she could reach. And she was incredible. It was just an amazing report. And when Rob got it, he couldn't believe it. It was as good as any of the undergraduates that he has. We've started running symposium programs now. We started one earlier in the year. I'd like to reach out and have teachers from around the world come and contribute to our symposium. We've been dealing with schools all over the UK. From Devon up to Lancaster, we've been dealing with this. I've been driving around all over the place and going on trains and things and talking over Zoom. And it's really a wonderful program. Rob has put out videos that can be accessed where he talks you through his expertise, which is astrophysics, and how to apply this. And basically, this is just, I was thinking, who does this benefit? And I thought, everybody. So just please get in touch and we can have a discussion. And there's our contact information. But in short, in my experience, this is a superb program. The students are so stimulated. And if I can help you in any way to have a go and get your students involved, please get in touch. And that's me. Bang on 20 past.
Thank you very much. That was impressive. So how many students you have working on this project?
Well, in my school, it's just a ridiculously high uptake. It's just fantastic. I say ridiculous, but in a great way. I've never had a club that's actually started or ended to develop more students over the year. Usually they fall out and get drawn off elsewhere to various things as other commitments come up. But no, we've had it grow. And we've got maybe a regular attendance of about 20, but that's just, there's a bit of turnover. So we may maybe have 30, 40 students who are actively engaged with it. And when we went to the Royal Society conference, for example, we had to choose 6 students to go each time. And it was totally unfair because we had to whittle them down. We have for most conferences, we have too many. We'd turn up and dominate it. But that's just my students, of course, Rosa. We've got students from lots of other schools. When we ran the symposium, we filled a large room full of students all doing it.
It seems to me quite advanced, what you're doing. It's amazing. Congratulations to that. You are preparing the junior astrophysicist. Quite complex. No, you cannot do that, unfortunately, in any place in the world. Well, you have a comment here on Facebook from Astrobotic Club saying, good job, works if astronomy and astrophysics are in the curricula. Yeah, for some people, if they don't have an astronomy club or a science club, or they cannot work in project-based learning, and it's not in the curriculum, it's more difficult. So we do have in some countries a little bit in the curriculum, but it's it will be difficult. In any case, we have to move on.